Okay, so what we're going to show in this video is, in some sense, a computational property of matrices. We're going to have three matrices, A, B, and C. They're going to be chosen of the proper size so that they will multiply properly and add properly, but what we're ultimately going to show is an effect that the distributive property for matrix multiplication holds, which is going to say that if we take a matrix A times a matrix B plus C, if you would add B plus C together first before multiplying, you would get the same thing as if you multiplied A times each of the matrices and then added together. Now, in order for the matrix multiplication and matrix addition to be well defined, we're going to let A be an M by N matrix and B and C be N by S matrices. Note the number of columns of A is equal to the number of rows of B and C, so the matrix multiplication would be well defined. And since B and C are both of the same size, when we multiply them by A, the resulting matrices will be of the same size and then can be added together. So the first thing we're going to do is to try the left-hand side of the distributive property expression, which is to say, rigidly look at those parentheses and work inside the parentheses first. So we're first going to add the matrices B and C together and then multiply by A. So what I've got here is just a carbon copy of the matrix A, and then I've got the matrices B and C having been added together. So let's go through the act of matrix multiplication, which we know is this row by that column, and let's just take this step by step. So when we take this first row times the first column, that you know that's going to be the 1-1 entry of the resulting matrix, and here that's going to be A11 times B11 plus C11, and that's going to go all the way down to A1n times Bn1 plus Cn1. And then we could work our way row by column, row by column, row by column, first row times each of the columns. Eventually, we would get out to the last column, and when we take the first row times the last column, this is going to give us A11 times B1s plus C1s. And as we're multiplying this row times that column, eventually we get down to A1n times, give myself a proper amount of space here, A1n times Bns plus Cns. Okay, so we've ultimately now multiplied the first row times each of the columns, and here's what we get. Then we multiply the second row times each of the columns, all the way down until you get to the last row times each of the columns. So what is this going to be? Take the last row times the columns. Here, this is going to be AM1, that's going to multiply by B11 plus C11, and as you multiply by the first column, eventually you're going to get AMN times BN1 plus CN1. Okay, no sweat. Now, that last row multiplied by the first column, then you take the last row times the second column, last row times the third column, last row ultimately times the last column. That will give you the entry in your product matrix in the last row, last column. And that's going to be last row AM1 times last column B1s plus C1s. And then you're going to take the next entry times the next entry all the way row by column until you get down to the last entry. That's going to be AMN times BNS plus CNS. And that is the product when we take A times B plus C, first adding B plus C, and then going through the product. You can see what the entries are. Okay, now we want to show what the result would be if we distributed first and then added. So now we're looking at the right-hand side of our expression, looking at A times B plus A times C. What is A times B? Let's take this and write it out. A times B, take first row times first column. That's going to be A11 B11 plus, well then A12 times B21 out to A1n times Bn1. And you could take this first row times every column of B and eventually you get to the last column of B, and when you would, you'd have the A11 times the B1S plus all the way out to the A1N times the BNS. So now we've taken the first row of A times every column of B, which then you could proceed downward and take the second column of A times each column of B, the third column of A times each column of B in that dot product fashion like we always do. Get down to the last row of A, you'd have to multiply now times every column of B. The last row times the first column in particular would be what? That would be AM1, B11, all the way out to AMN times BN1. And you could take that last row times each of the columns, and eventually the last row would multiply by the last column, and that would give you what? That would give you AM1, B1S, all the way out to AMNBNS. Okay, sweet. So we've we've multiplied A times B. Now we want to add in A times C, and we can compute A times C simply by going through the computation. Here now we're taking the matrix A times the matrix C, as we always multiply matrices row by column. So multiply the first row of A times the first column of C. You're going to get A11, C11, and then eventually down to what? End of the first row of A is going to be A1N, end of the first column of C is CN1. And then you take the first row of A times each of the columns of C until you get out to the last column of C. And when you do, what are you going to get? You're going to get A11, C1S, all the way out to A1N, CNS. Okay, so now we've taken the first row of A times each of the columns. You know then you could take the second row of A times each of the columns. You could take the third row of A times each of the columns of C. You could go all the way down until you got down to the last row of A times each of the columns of C. So in particular, let's take the last column of our matrix A times our first column of C. What's that going to yield? That's going to yield AM1, C11 out to MN, CN1. And now we can take that last row times each of the columns. Eventually we're going to take that last row times the last column. And when we do, we're going to get AM1, C1S. And that's going to go all the way out to AMN, ran out of space, times CNS. So we write in our CNS, and here we go. Now we've got AB plus AC. And what do we ultimately want to hope to make a connection to show? We want to show that A times B plus C, in effect, what is in this Roman numeral 1 row is equal to AB plus AC. What is down here below? And so above, we did the A times the sum of the B plus C, and you see what the matrix is. And down below, we did the AB plus the AC. But check it out. When you look at these two situations, my claim is that these two things are equal, and check it out, it is indeed true. Because when you add these two matrices together, what are you going to do? You're just going to take the entries in each corresponding position and add them together. And what you notice is every entry in the first, in the 1-1 position of AB and the entry of 1-1 AC, they all have the same A's with corresponding C's and B's. And when you add them together, the A11 is essentially going to be multiplied by a B plus C, and the A1N is going to be multiplied by a B plus C correspondingly. And then you can look, whenever you go out to like the top right entry, you're going to have the A11 through the A1N multiplied by corresponding B's and C's of the same indices, which whenever you would add those terms together, you could redistribute them just like you would redistribute good old-fashioned numbers, because that's what they are. And then you get the following that is written up above. It's precisely the same in the top right entry. And in the bottom left entry, you would have the same story, right? Because you've got the A1M1 to the AMN all multiplied by the B11 to the BN1 and the C11 to the CN1. And that's precisely what you have in the other matrix, or in the other matrix above. and then you do the AM1 to AMN times B1S to BNS, which is the same story here, AM1 to AMN C1S to CNS, which when you add those two things together, the AM1 is multiplied by the B1S plus C1S out to the AMN being multiplied by the BNS CNS. So the long story short is whether we add together inside the parenthesis first and then multiply by A, or whether we distribute the A and then add, the result is the same. And the long story short, in effect, and something now that we can take with us for the rest of this course and frankly for the rest of our lives, is that matrix multiplication abides by the distributive property.